All right, wave-particle duality. Not going to get into this too much. Wish we had more time to talk about that. Wave-particle duality just kind of gets into this interesting stuff where light and electrons sometimes act as a particle or a wave. So the infamous double slit experiment, which is our evidence that electrons and light act as a wave. And then we've got Einstein's photoelectric effect, which is our evidence that light acts as a particle. So it's pretty crazy. And we don't have time to get in all that interference and all that good stuff. But anyway, what we do need to do is get the equation that Einstein got out of the photoelectric effect, because we are going to need this tonight. And this is the equation. I would write it down. Energy is equal to Planck's constant times the frequency. Again, we use an F instead of a V these days. And I think they just do that to print new textbooks. I would not write this down. I like to solve for the frequency and then solve for the wavelength. So I like this guy, E equals HF. E equals HF, where energy is equal to some constant called Planck's constant. That's the H, times the frequency in hertz. Planck's constant's right down here. You may as well write it down a while as well. And that is 6.626 times 10 to the negative 34th joules times seconds. That's 6.626 times 10 to the negative 34th joules times seconds. So write down E equals HF, and H equals 6.626 times 10 to the negative 34th joules times seconds. Please get those two things down because we will need them this evening. This equation comes out of a very important experiment that Einstein did called the photoelectric effect. This is actually what he gets the Nobel Prize for. He did not get the Nobel Prize for the theory of relativity, both special and general. He did not get the Nobel Prize. Well, he should have gotten probably 2 or 3 Nobel Prizes, but the only one he got was for this one. So yeah, cool. So let's work that new formula. So I'd like you to calculate the energy of orange light emitted by a photon in a neon sign that has a frequency of 4.89 times 10 to the 14th. So what are you going to do? Well, you're going to use this new equation, E equals HF. And H, I'm going to type it before I butcher this. H is 6.626 times 10 to the negative 34th joules times seconds. So go ahead, copy that down, try it, see if you can't solve for that energy. Go ahead. So let's do this guy. Here we go. This is just kind of plug and chug. Energy equals Planck's constant, 6.626 times 10 to the negative 34th joules times seconds times the frequency, 4.89 times 10 to the 14th hertz, which is a cycle per second. Seconds cancels out, and we are left with joules. So 6.626, whoops. 6.626 E negative 34 times 4.89 E 14. We get 3.24 times 10 to the negative 19th joules. So a photon, one single, I know that seems like a really small number, but this is the energy of a single photon, single packet of light. It's very small, 3.24 times 10 to the negative 19th joules. You get a mole of photons. So a mole of photons is actually called an Einstein. So if this said, what would be the energy of an Einstein or a mole of orange photons? Well, this is joules per photon, right? So if we wanted to do energy per mole of photons, we would multiply by Avogadro's number. There's 6.022 times 10 to the 23rd of anything in a mole. Could be electron, could be atoms, electrons, molecules, photons. So photons per 1 mole. And if we do that, 3.24. Now, again, this is an extension. Then in the lab, we'll actually talk about this tomorrow. I think one of the post-lab questions has you calculate the energy of an Einstein. So this, an energy of a mole of orange photons. Now we're talking. That's 195,000 joules per mole. And we could divide that by 1,000. we would probably write that as 195 kilojoules per mole. So just so you can see some conversion, some jumping around here, right? You know, yeah, just kind of, but let dimensional analysis guide you, right? This is the energy of one orange photon. We multiply by Avogadro's number. That's the energy of a mole of photons. Fantastic. All right, man, we have got to talk about Niels Bohr's model. And before we do that, we should review where we're at before Bohr comes into play. And you're going to see how all this beautiful math and talk about light that we did tonight, how that's going to tie into Bohr's experiment. You'll really see it tomorrow night. So great. It's the nice thing about the summer. You learn the stuff and then bam, lab on it right away. You know, no waiting, no delay, no hesitation, right into it. All right. So if you'll remember, John Dalton said the atom was a solid sphere. And then J.J. Thomson said, nah, the atom is a positive jelly with some negative electrons embedded in it. That was the plum pudding model, right? And then Rutherford shot that out of the ballpark. He said when he did the gold foil experiment, Rutherford said, nah, there's actually a massive thing in the center called the nucleus where the positive charge lives. And then he said that the electrons are just randomly distributed around it. And that's where he went wrong. So with Rutherford, we got up to the nuclear model. Okay. But what Bohr is going to do to improve this is Bohr is the first person to say those electrons, it's not just random. There actually is an order to it. The electrons can only be in specific regions around the atom. So Bohr's model, which I'm sure you all saw in high school, right? Bohr's model, Niels Bohr, his model of the atom is we've got a nucleus. He said, Rutherford, man, I love that nucleus. But then he said the electron can only be in certain regions around the nucleus. Now, Bohr's downfall is he thinks that all of these regions are spherical. You got to remember, when we draw the atom on a two-dimensional board, it's easy to think of the atom as this flat thing, okay? But it's not flat. It's a sphere, right? The atoms live in the same three-dimensional world that we live in. So they're not flat. They're spheres, right? So anyway, you know, this is Bohr's model, which we're going to get into in a moment. We're going to talk about the experiment he does to figure this out. Because it kind of looks like a miniature solar system, right? It looks like sun in the middle and the planets going around the sun, right? Okay. Oftentimes, this is called the planetary model. So I'm going to talk about how does Bohr figure this out? How does Bohr figure out that electrons can't be anywhere, that electrons can only be in specific regions around the atom? Well, what he does is he uses something called atomic emission spectroscopy. And here we go, folks. This is some heavy stuff. This is the beginning of quantum mechanics. Here's Bohr's idea. Bohr, very brilliant scientist, like insanely brilliant. And Bohr does a lot of this in his head. He was actually not a good experimentalist. So it's kind of funny. You think about the most important names in science, the household names in science, you know, in the last 100 years, and it's these theoreticians, right? They're not really good at doing the science. They're good at sitting and thinking about the science. Einstein, not good at doing experiments. Bohr, terrible at doing experiments. Oppenheimer, really just a good, not he was terrible in the lab. These guys are it's like a new wave of science where you just sit around, think about stuff, and do some tough math. Anyway, here's what Bohr thought about, and then really somebody else did a lot of the experiments. Bohr thought, okay, the nucleus, according to Rutherford, is where all the positive charge lives. Now, we also know that neutrons live there as well to kind of stabilize the mass of the atom. But he says, okay, positive charge lives here in the nucleus. He says that these negative electrons that are whirling around the atom, remember these electrons here, they are negative. He says they are going to be attracted to the nucleus. He says, think about it, right? Opposite charges attract. So he says the electron is going to be happiest when it's as close to the nucleus as it's allowed to be. And he actually comes up with a term for this. He calls the closest that an electron is allowed to get to the nucleus, he calls it the ground state. And that's going to be the lowest energy conformation of the atom. That's when the atom is going to be most stable, when that electron is as close to the nucleus as it can get. Now, it's very sad. It's like, the saddest Romeo and Juliet. It's like the original Romeo and Juliet, right? The electron and proton, they love each other. They're opposite charges, but they're never going to be allowed to be together. And that's because there's a different kind of physics at work here. There's a strong and a weak nuclear force in the atom, and that prevents the negative electrons from being sucked into the nucleus. Okay, but anyway, don't worry about that for now. For reasons we won't get into, the electron cannot get any closer to the nucleus. So then Bohr gets an idea, and he says, he says, if we zap the atoms full of energy, so if we pump in energy, how could we pump in energy into these atoms? By the way, we're just talking about hydrogen right now. How do we know this is hydrogen? Well, because there's one proton and one electron. So it's hydrogen, or it's a neutral hydrogen atom. Bohr gets the idea that if we zap this full of energy, where could that energy come from? That energy could come from heat or electricity. He says if we heat these atoms up or zap them with 100,000 volts, we are going to cause that electron to move. The atom is going to absorb the energy. And there's only one thing that can move, and that's the electron. So it says if we put energy in, the electron is going to move away from the nucleus. So when energy is absorbed, okay, by the atom, the electron moves away from the nucleus. I'm going to give you a second to catch up and write that down. Absorbing energy, the electron moves away from the nucleus. Okay, and here's Bohr's idea. Bohr says, all right, well, if Rutherford is right, and the nuclear model of the atom says the electrons can be anywhere, then Bohr says, if I zap the atom full of a whole bunch of different packets of energy, so if I take a mole of hydrogen atoms and I put in a lot of energy and a little energy and a medium amount of energy and everything in between, then I should be able to, in this sample of hydrogen, I should be able to send the electrons. If I put in a little bit of energy, I'll send them not too far from the nucleus. And if I put in a little more, I'll send them a little further and a little more, a little further, and a lot of energy that's starting to get out of here. And I put in a whole bunch of energy, the electron starts to get this far out from the nucleus. And if you put in too much energy, eventually you kick the electron out of the atom. And that's called the ionization energy. So the ionization energy that's the amount of energy needed to kick the electron completely out of the atom. Amount of energy needed to kick the electron completely out of the atom. Cool. So, recapping, here we go. Bohr gets this idea. What if we take a whole bunch of hydrogen atoms? What if we zap them full of a whole bunch of electricity and energy? And what we should be able to send the electron, if Rutherford's right, we should be able to send the electron anywhere. He calls these regions where the electron has been moved to, he calls them excited states. Because the electron has been excited. Now, it's funny, the electron is not excited about being out there. Because if you stop and think about it, the electron does not like this. The electron wants to be as close to the nucleus as it can be. It loves the nucleus. They're opposite charges. They stabilize one another. Okay? It does not want to be sent away from the nucleus. So it's not excited about going to an excited state. It has been excited out there. Okay? Okay, so here's the brilliance of Bohr. Hopefully you're following along so far. Bohr says, okay, we send these electrons to these excited states, and here's what's going to happen. These electrons don't want to be out here. They're going to want to come back down. But when they relax back down to the ground state, whatever energy they absorbed, they're going to have to emit. So Bohr gets the idea that, hey, if we zap these hydrogen atoms full of all kinds of different energy, when the electrons eventually come back down, they're going to release light. They're going to, or emit light. That's the more scientific term. So here's Bohr's idea right here in a nutshell. Here we go. He says this. He says if Rutherford is right, and we do this with every different packet of energy we can, then I should be able to send the electrons to all these different areas, and I should get every color of the rainbow. The electrons that I don't send very far, they should give me my reds. So when these electrons come back down, this is where I should get my reds. Then I should get my oranges. Then I should get my yellows. Then I should get my greens and my blues. And then finally, these highest energies should give me my indigos and my violets. So his idea is that if I look at the light that comes off of these excited hydrogen atoms that are relaxing back down, if I look at that through a special prism, because you got to imagine, if all this is happening at once, you're going to get white light, right? Because all the colors of light merge together to make white. But if we pass that light through a prism, you should get the whole rainbow. Now, the prism we use in the science lab is called a spectroscope, okay? And it uses a spectroscopic film, but essentially it's like a prism, breaks it up into the light. So Bohr's idea says, okay, I'm going to take a whole bunch of hydrogen atoms. I'm going to excite a whole bunch of electrons. I'm going to let them relax back down. I'm going to look at the light that comes off of it. And if I get a rainbow, Rutherford is right. The electron can be anywhere in the nucleus. It's totally random. So he does this. And you know what you don't get? You don't get a rainbow. Here's what you get if you do this with hydrogen. And you are going to see this in the lab tomorrow night. It is so exciting. People love this lab. This tends to be one that people remember. And it is kind of crazy. You're going to see a Nobel Prize winning experiment tomorrow night. I mean, I get excited about it still. Here's what Bohr sees. When you do this, and you do it with hydrogen, you see three colors. You get one shade of red. You get one shade of aquamarine. So an electron somewhere out here coming back down. And you get another shade of violet. So an electron really far away, making a big transition. And Bohr, and this turns out to not entirely be right, but here's what Bohr's idea is. Bohr says, well, there's only one explanation. If I don't get all the other colors, then I must not have been able, I don't get every shade of red. I must not have been able to send the electron everywhere. I must have only been able to send it there. And if I don't get every shade of orange and yellow, I must not have been able to send the electron. I only got that one shade of aquamarine. I must have only been able to send it there. And since I only get that shade of violet, I must have only been able to send the electron right there. And then Bohr says, well, this is obvious. I must have, if I'm only getting that red line, I must have only sent the electron here. Okay, and if I'm only getting this aquamarine line, then that would correspond to the electron being sent here. And then if I get a violet line, then that would correspond to the electron being sent here. And this is how his experiment leads him to believe that orbitals exist. Because when you excite atoms, you do not get a continuous spectrum. You get what's called a line emission spectrum. A line emission spectrum. All right. Let's take a look at the slides and I'll show you what I'm talking about. So here is the line emission spectra for helium. And here's the line emission spectra for barium. So you can see this is the full continuous spectrum. This is what you get if you would point a spectroscope at the sun or an incandescent light bulb, one of those old school light bulbs that has the tungsten filament that glows. They're kind of illegal now, right? Okay, but you get the full Roy G. Biv spectrum. That's what should have happened if Rutherford's model was right and the electron could be sent anywhere. But we don't get that. We only get specific lines. And it turns out upon more inspection that this is actually what's going on. What is actually happening, and whoever drew this did a bad job. We'll talk about that in a second. But the violet line, it turns out, is actually an electron going from the 5th energy level down to the 2nd energy level. It's a 5-to-2 transition. The aquamarine line is an electron going from the 4th to the 2nd. And the electron going from the red line in the hydrogen emission spectra is an electron going from the 3rd to the 2nd. So tomorrow night, you will see this in lab. For hydrogen, you only get 3 distinct visible lines. You get a violet, an aquamarine, and a red with these specific wavelengths, which we're actually going to calculate momentarily. Now, here's why this drawing is not so good. The orbitals actually get closer together as you go further out. So it turns out, like if I have my nucleus, here's my first orbital, the distance between the first and second orbital, that should be the biggest. And then the orbitals should start getting closer together as they go further out. They're going to they start out pretty far apart, right? Big gap between the orbitals, and then they start to get closer together. This artist drew it backwards. It's literally backwards. So anyway, this person was doing a better job. See, they're showing a big energy gap between the first and second, and now a smaller gap. So this person at least knew what they were talking about. All right, feeling good about that, feeling good about that. The Rydberg equation, oh my goodness. Are you ready? I don't know. Let's do it. Here we go. Let's just write this thing down. So it wouldn't be chemistry if there wasn't math. So after Bohr figures this all out, he figures out how to do a bunch of crazy math with it. And you can actually predict the wavelength of light associated with an electron going from the 4th to the 3rd orbital, and from the 4th to the 2nd orbital, and the 4th to the 1st orbital, and all this stuff. So the first thing I want to mention before we get that equation, and this is a common misconception, if you send an electron to a higher energy orbital, let's say we send it out here to the 3rd orbital that I've drawn, that electron has options. That electron can relax all the way back down to the ground state, and it could do an n=3 to an n=1 transition. The ground state is n=1. But it could also just go to the 2nd and do a layover. Where is that actually the 4th, right? 1, 2, 3, 4, so n=4. If I send an electron out to the n=4, the 4th orbital, it could come all the way back down to the 1st, to the ground state, but it could also stop at the 3rd. It could go to the 2nd. It could go, so it could, it doesn't have to come all the way back down. And when it does that, it can release smaller amounts of energy. So if it goes from 4th to 3rd, it's going to release a smaller amount of energy. This would probably be like a red, right? And if I do a big jump, n=4 to n=1, I would get like a higher energy wave, which would be like violet. In fact, all of these transitions are happening. If I go back to the hydrogen emission spectra, well, here, let's do this one. It's important to understand that all of the possible transitions are happening. There are electrons getting sent to the 2nd orbital and coming back down to the ground state. But we don't see this because this is such a big energy gap that that's actually in the ultraviolet portion of the electromagnetic spectrum. So we can detect it, but you won't be able to see that transition because the human eye can't pick that up. And then maybe like a 4 to 3, that gap might be too small that it would be infrared. So all of the transitions are happening. We only just get lucky to see a couple of them where the energy gap falls in the visible spectrum. Too big of a gap, ultraviolet, too small of a gap, infrared, and we can't see it. So